Okay, hello everyone. Hello Quantum Developer, hello Antonin. Okay, so last time so in the last episode stream we built this program here. Basically we implemented projection and a view transformation, so now we have actually a 3D scene. But yeah, maybe as you can see, it's not really nice looking. And also here's the code. Is this big enough? If it isn't, you can tell me in the chat. So as you can see, this is the mesh data. So yeah, it's hard-coded, and that's not really useful. So of course we want to create an object in Blender, for example, and then we just want to use it in the program, and we don't want to hard-code the positions of each point vertices. Hello Gaga Pro. And so that's why I want to implement model loading. And my idea for that was because, okay, so first of all, maybe we can create an object here in Blender. I hope the stream isn't frozen. I think it's working. But if anyone else has problems, then yeah. Okay. All right. So yeah, I first want to create an object here in Blender. So I mean, we can just use the default cube. So if I export this, I like to use OBJ as a format. Because I think it's, well, we will see. But of course, I often also just want to load triangles. So what I often do is just triangulate the mesh, so it doesn't export like faces with 4 vertices, but instead it only outputs triangles. And if I export this here as cube.obj, we can look at the file in more detail. So here's the file. Okay, that's very small. So basically OBJ is a really simple format. Or maybe it can do more difficult things, but for our purposes, it's really simple. So the cube has 8 corners. So in the OBJ file, there are also 8 positions. For each corner, there's a position, and these are specified with the V for vertex. And then there are other attributes, such as the vertex, the normal, for example. So the normal is like the direction in which the face is pointing. I think we can even I think there was a way in Blender to show the normals of a... Okay, I don't know how this works right now. Maybe, wait. So I think I have to be in edit mode and then... yes, hello Karim. I will get into lighting after the model is loaded, basically. But I'm not sure if I can make do shadows today, because that's a bit more difficult. But I was planning to do basic lighting today, yes. So this is the normal of each face. It points in the direction of the that is perpendicular to the plane of the face. And yeah, these are specified here. And the cube has just 6 faces, so there are only 6 normals. And then there are also texture coordinates, but these are not, I don't think we will use them. Okay, so the thing is, more advanced lighting than Phong is a bit difficult. But there is a website which explains this. So there is something called, yeah, PBR, but I won't implement this today because I think this would take very long. So, I mean, you could read this. Basically, physically based rendering or physically based lighting makes the objects look really realistic. But today I only want to implement Phong, but we'll get to that. And then in the OBJ file, so we have the positions, the face normals, and finally, because we want triangles, in the OBJ file there are all triangles specified. So basically we have a face, and this is specified by 3 vertices. The index of the position, so the index into one of these, and then the index into one of the texture coordinates, and then the index into the normals. Yeah, so because, wait, let me draw this. because this is what what part of the cube looks like. And if we have this triangle, for example, and this one here, this vertex here is now shared by two triangles. So by this triangle and by this triangle. Of course, there are also other triangles, but I want to focus on these two now. And this one has a vertex normal, has a face normal, which points in this direction, and this points in this direction. So the triangle, this point here, can't share all information because which normal should we specify for this point? And this is why these indices are used here, so we can mix positions and normals to create all kinds of triangles with the correct normals. Yeah, but that's the basics of this format. And we could now parse this by hand. And this is what I did in my game, actually. I think I have this here. Or maybe... Yeah, so I wrote this function load in my game. I wrote this function load mesh, which basically opens the OBJ file. Opens the OBJ file and then goes through each line and checks whether there's a T, whether there's a there's an F. Like it checks which line it's reading, and at some point it then reads these positions and stores them. But writing this is a bit like, you can make a lot of mistakes with this. It's certainly possible, but I would make a lot of mistakes and it would take very long if I would do this on stream, which is why I want to use a library for the loading of the mesh. And there's a library called tinyobjloader, which I want to use. And yeah, basically you just tell it the OBJ file you want to load, and then you can ask it then you can iterate over the faces and extract the positions and the normals, and that's a bit easier than writing this from scratch right now. So this is why I want to do this. And also I don't actually think if you write a game, if you want to like ship the game, I don't think you would even want to load an OBJ file, because that's really unnecessary. You could just write the data of the file into a binary file, and then the loading is much faster. So in the end version of the game, I wouldn't even use OBJ files. I would just load the stuff from memory from a binary file, which is why I wouldn't recommend to put that much work into writing an OBJ parser or worrying about this. Yeah, but okay, let me close this. Yeah, let's start. So I want to add this repository as a submodule to the Git project. And I have to look up how to do this because I forget every time. Okay, I need this command. And now the stuff is downloaded and added to the submodules. And why this library is so, one nice thing about this library is, even though there are a lot of files in here, the only really important thing is this tinyobjloader, because this file contains basically everything. So the only thing I need to do is include this here. And I need to use the correct path. So tinyobjloader is the directory name. And the header is called like this. Yeah, and maybe that already works. Okay, so it didn't complain that it couldn't find the file. So the next step would be to use some of the stuff in the library. Right, I want to open the file. Oh. Okay. So there's a lot of stuff in the file. But it's really nice because on the GitHub side there's a basic usage example. Okay, so it seems like they have a deprecated API and a new one. So I want to use the new one because I don't know if this will work in the future. Okay, and because this is only a header file, what these single header file libraries often do is they write all of the code in the header file, but because it's not optimal if header files contain all the source code, they let you decide whether you want to include only the function declarations, like these empty, for example, here's a function, but there's no implementation. Basically, that's what you would put in the header. And yeah, so, and way below that, there's the implementation of all of these functions, and they are guarded by an implementation macro. Yep. And in this case, I want to use the implementation, so I want to define this. So if I define this before this file, then all of the implementation will be included. Otherwise, the declarations are still there, but when the linker links everything, it won't file the implementation of the functions, and it will throw an error. So yeah. And the way how to use the library is now we have to define this OBJ reader. So it's an object-oriented library or API. And maybe we can write a separate function for that. And of course I want to give it a file name, pass it a file name. And then, so first I define this object here. And then I let it parse the, wait. So the input file, okay, so here is just a string, a file name. And reader config. I don't think we will, because somehow you can also export materials using OBJ, but I don't know what this means actually. So I unchecked this and we don't need this. Yeah. Okay, let me just about shape matching in physics. I don't know. We will see when I implement the shape matching thing. So I can't tell you that right now, sorry. Yeah, so this is a bit of error checking. And maybe there are also warnings which we can copy. And now comes the important stuff. So I will now, no, I will not copy this. So I tried this once. So I looked a bit into how this works. But I'm not a professional at using this library. But so basically there are shapes. And a shape is this here, for example. So our cube is a shape. So the entire cube is a shape. And I assume you can export multiple objects in a single OBJ file. So that's why there are basically you can get multiple shapes. So the reader reads in all different shapes. Yeah, so get shape. Yeah, so you can get you can get a vector of shapes. I don't like to use this auto because then I don't know what the type is. And materials we don't need. So we have the shapes, and in each shape so first I want to assume that the number of shapes is 1. And if I only want to load obj, I only want to load obj files where there's just one shape in it, because otherwise it would be a bit I would need to handle other stuff. So if I want to use multiple shapes, I would just call this function multiple times. So in this case, I want to return an error. So like the function returned an error. And now, so that means now we only have one shape. And as you can see, there are a few members here. So first of all, there's the name, which I assume is this. And then there is the mesh. And I think the mesh is the important part. Yeah. So basically on the mesh, we can then let's print the name of the shape. So I think maybe we can also try this out right now, so we don't get a bunch of errors at the end. And the program should run in this directory, so I can directly access the file here. Yeah, let's try that. Okay, we have to use the namespace. Because we want the first shape. And of course I need to return 0 if there are no errors. And yeah, so the name of the shape is this thing here. As you can see. Okay, now I want to iterate over the faces of over the triangles. So we can look at what this mesh here, what is in this mesh here. And so first of all, there is a vector that defines how many vertices are there for each phase of the mesh. So basically in this vector here, the number of elements in this vector are the number of phases. And because I triangulated the mesh, there are only 3 vertices. But I want to ensure that. So I want to iterate over these and want to check if they are always 3 and otherwise return an error. So let me check if I defined. Oh, okay. Shapes.mesh and then shapes.mesh, this is here, and then num phase vertices dot size. Yeah, hi scene. I actually don't know how to pronounce that. And I have seen a video about Jellycar too, and I think it was really interesting to watch how he implemented the physics. But he didn't exactly talk about how he solved the constraints, or at least not in the video that I watched. So yeah. Why is the face divided to three triangles? No, so the face is one triangle, but like this is a vertex here. Maybe I said that wrong. So the face is a triangle because it references three vertices. So yeah, the face looks like a triangle. Okay, so now I want to check if each of these is 3. And if it isn't 3, then I want to return an error. Maybe something like this. Okay, I misspelled. That's not good. Oh, I want to check if it isn't 3, of course. Yeah. Okay, so because there are only triangles, this check passes. So we can continue then. And yeah, maybe return 1 in the other cases too. So yeah, whatever. And now I want to iterate over the faces. Let's see. Yeah, so this is an index into the position. This is an index into the texture coordinate. And this is an index into the normal array. I hope this makes sense. Yeah, but we need to iterate over the faces again, so I can just copy this loop. And now I want to iterate over. I mean, I'm basically doing what is. I'm basically doing the same thing as here. So it varies when. Yes. But I think that's the only. I think OBJ also supports a color, so you might have a array of colors here as well. So then there would be 4 indices per vertex. But I think there aren't really more than position, normal, texture coordinate, and color. Yeah. Okay. And so because so let's make the second loop over the, so basically this is the face index, or it's the triangle index. So we can call it like that. It's a bit easier to understand. And then this is the vertex index, but let's just call this I. You know, I always have to think about whether I want to use descriptive names or short names. Yeah, so because each face has 3 vertices now, because we checked this here, and we can just hardcode a 3 here. And yeah, then, so what we want to do now, we need we define the vector types here. So we need a vector 3 for the position and a vector 3 for the normal. And now we need to load them. And I mean, this looks really complicated, but I don't think it actually is very complicated. So the way this works, a tiny OBJ loaded the indices too. Let me think. So, wait, I need to think. Yeah, maybe I should think about what I want to get out of this function. So I want to get an object, a struct mesh, and that's the object that I want to render in the end. I'm probably not going to draw with indices, draw elements, because so maybe it is possible, but I think it's a bit more difficult, because now, like I try to explain here, this vertex, it shares the same position for many triangles, but the normal is not shared for every triangle that shares the same position. So it's hard to combine these with indices when you render them. So it's easy if you differentiate between each type of attribute that you have. So if you have a position, like it's here, but I think with GL elements, GL draw elements, you have to just specify one index. Although maybe it's possible to specify multiple indices, but I'm not sure. So this is why I will just copy the vertex. So I won't use draw elements. But doesn't your OpenGL already take care of duplicating the relevant vertices? No, I don't think it does. I think it actually just loads what's in the file. So that's why vertices is like vertices only contains the positions. Yeah. I think it doesn't handle the duplication. Anyway, so I want to okay, first of all, I want to define a type for indices, because I don't like int, because you don't know what size it is. So that's very, very confusing. But there is a header in the C standard library, which gets you the integers of specific sizes. So for example, int32. So I want to include that. And then what I like to use is I like to define these to a bit shorter names. So U32 and U36. So they are a bit faster to write. Yeah, so and in the mesh structure, I also want to, I just want to copy this information into the mesh structure. So I have an array of positions. And yeah, to make this an array, I want to just store a pointer here. And then I want to make an array of normals. And yeah, so we also need the respective sizes. So position count. And then normal count. Yeah, and I think that's all I need to store right now. And I also, so besides the vertex information, I also need to store the indices. So maybe let's do another struct for that. yeah, so mesh index, or maybe mesh vertex is better. And basically I want to store the position index, the normal index, and yeah, that's everything I need right now. And then I need the triangle count. So basically this here will have the size of triangle count times 3. So for each triangle there will be 3 indices. And I think this is pretty usable. Yep. Okay, so let's use the memory. Right. So this 0 initializes the struct here. And I want the mesh to have the number of positions is equal to yeah, and that's the other thing. So we have this mesh structure, but actually the mesh doesn't store any of the positional, or like everything that's stored here isn't actually stored in a mesh. So OBJ stores this in this attribute struct, which is here. And that's where all the vertices are stored. So the number of positions is in this struct here. So what this says is that we have an XYZ for each vertex. So if I take the size of this vertices and then the size of that, then we have 3 times the amount of vertex positions. So we need to divide this by 3. And the normal count is pretty similar, I think. Yeah, so the normals are here. And we also have, I mean, I guess it's also XYZ. And that's everything for now. So now we need to look at this mesh thing here again. And the way this seems to work is so we access the indices and Yeah, so it gives us an object. Basically, it gives us an object that represents all of these here. So we need to, we have three of these indices per triangle, so we need to skip 3 times the triangle index, and then we need to add the actual vertex index we are interested in. And the result of this is an index t. And as you can see here, so that's where we get the vertex index, normal index, and text code index information. So index t. And to get the position and normal information out of this right now, basically, okay, so we need to access the attributes again. And because this array here maybe it's actually easier to just copy this stuff here. So I first want to allocate the memory for all of these mesh positions. So now I have the memory for both of these, and I think we can just iterate over them. Yeah, so now we can get each of the x, y, z values out of the vertices here. And I need to look up how I create a vector here. Okay, so this is the... So the reason I'm not doing this here right now is because it's not really necessary. All the vertex information we want to store is already in this array here, so we don't need to iterate over the faces to get them. We can directly just copy this buffer here. And I think that's a bit easier. So to get the position, we just have to because that's the number of positions, and we divided this here by 3 because that's basically the x, y, z for each position. And here we count only the index of the position, so we need to skip 3 of them and basically have to add them individually. Yeah, but I think this can work. So, and then we go to mesh.positions, add I, and then we just input the position. And we can do the same thing for the normals. And I think it was just called normals. Yes. Okay, so now we have the position and normal information stored. And the last thing we need to store is the indices. Yeah. So maybe it's even more understandable if I name this mesh face, and basically we create this mesh here, and then we only have position indices. So because we have a triangle, we have 3 of them indices, and we have 3 of them here as well. So I think this is a bit easier to understand. So these are triangles, maybe. Okay, mesh triangle and mesh triangle, like this, and yeah. So then the mesh dot triangle count is equal to the number of faces, and we just check that each face has only 3 vertices, so this works. And here we now need to copy the indices, and of course we can, because we set this right here, we can also just write this triangle count. So basically we want to create one triangle. And then we want to store this in the mesh. Triangles, add triangle index is equal to triangle. Okay, so we just need to store the stuff of the triangle right now. So we don't need this anymore. So for each vertex, we now need a triangle dot position indices and triangle dot normal indices. We need to set this. So basically we need to copy these values here. And now I need to look at how these are stored. But I think that's already correct. Yep. obj index dot vertex index. Because this index here, it seems that it's actually the index of the vertex position, because to get all the all 3 of the position components, it just multiplies it by 3 and then adds the respective x, y, z offset. So if I just use this index here, this is already correct, it seems. And of course, this doesn't work if I don't allocate the memory for this. So triangles. Triangle. And the number of these are just mesh.triangle count. Yeah, so I think this converts the tinyobj stuff into the structure here. Yeah, so I think this works. So the last thing I need to do is output the mesh. So mesh, I don't know, out mesh or something. And I need to write this out. So because we created this mesh here locally, and we need to pass this here. So basically cube mesh, for example, and then we just pass this here. And now this should load our mesh. So the second thing, so now we basically have this, I mean, I can't really, well, I guess I can test this. Yeah, I can output this to test it. Cube mesh. I need to split this file up, but not right now. So position count. So I want to output the positions right now. So yesterday is the out cube mesh. Yeah, so that's what I will get to now, or after I check if this is correct. Positions. So, and the reason I'm storing this like this, the mesh like that, is because, for example, if we somehow in the future implemented a soft body with this, it's really hard to implement a soft body if we only have triangles, because when we only have a bunch of triangles with basically duplicated positions, then it's really hard to, well, how do I say this? So because when we only have triangles, so for example, we have this triangle here, we have this triangle here, and we have this triangle here, then this position will be there 3 times. So, but actually it's just one position. So it's really hard to simulate this when we have 3 positions, but we actually only have 1. And this is why I also want to store the mesh in this format, because this way we could, for example, use a struct soft body. And then we just make another array positions, which matches the dimension of this array here. But we use this array for rendering. So we only have distinct points in this array. And then we can just ignore the static points and update these in the simulation. And then it's really clear which point, so there are no duplicated points is what I want to say. Yeah, the triangle would probably fall apart. The triangles. Okay, so we output the positions. And the normals maybe too. And lastly, we can output the faces. Triangles. So this I need to extract. Triangles. Yeah, and I could print this now like here, something like there. So oh, I need to, I is already taken. Position indices and normal indices. I think this might work. So wait. So like this and then end line. Okay, I hope we don't get a segmentation for it. Or a bunch of errors. Okay. Normal count, that's wrong. Yeah, normals. I forgot the comma here. Probably here too. Position. Okay, and the namespace error. Okay, let's see. Well, okay, yeah, okay, the stdout function, the print function of a eigenvector looks pretty weird, but yeah. So at least we can compare the indices of the faces. And the weird thing about OBJ is that the indices start at 1. So basically 1 means this here, which is kind of strange. And I don't understand why you would do that, but that's just how it is. So the indices get translated correctly. So the vertex index 5 is the, when you count with 0, is the 4th. And then 0, and I think this looks correct. Maybe the last thing. Yeah, so I think this worked. I mean, I assume the normals and positions work too. Looks like it. Okay. So now what I want to do is yeah, convert this. I'm not sure because I don't But don't you have to copy the positions of normals into a new array when rendering? Yeah, so I will talk about this now. We need to copy them. So it might be possible to keep them separated, I think. So you could create two vertex buffer objects. And yeah, so wait, let me draw this. So previously, what we did was, and let me see where this is exactly. Yeah, so previously what we did was, we had a single vertex buffer object. Or VBO. And in there, so basically the data we put into this vertex buffer object is this here. We put a position, the first position, then we put a color. So position here, color 0, then the next position, and then the next color, and so on. So we only had one vertex buffer object. And then we told OpenGL down here what this data means. So basically we said, okay, first of all, the vertex is 6 bytes long, 6 floats. So this is one vertex. And then we said, okay, so the first thing is the position. Okay, we didn't say it's the position, but we specified how long this attribute is. And then we say the second one is here. And I think we could actually create two vertex buffer objects where we just store the positions and so on. And the colors here and so on. So then we would so yeah, I think this would work too, but I'm not sure and I don't want to experiment right now because yeah, I hope that's understandable. So what we are going to do instead is basically this here. So, but we don't use a color. Instead, we will use the normal information here. So this is what I want to create right now. Yeah, I think that's it really. Oh yeah, and to create this, basically we loop over the vertices, over the indices, and then we just construct this buffer. But maybe I will just implement it and it's a bit more understandable this way. So let me think about how we can call this. Maybe mesh to OpenGL or something. So we input a mesh and yeah, let's see. So I want to copy this stuff here and edit it. So we definitely need a vertex array object which stores the state and like the how the vertex buffer object is laid out and the vertex buffer object itself. And yeah. I need to think a little bit. So I want to create these inside of the mesh. So this way we would say we generate the vertex buffer object and the vertex array object, and then we bind the two. And so here's the thing I like to do. What I often like to do is just tell OpenGL how large the buffer is. So basically we have to calculate this now. Yeah, how large will this buffer be? Well, we have okay, this is already, we have the size of one vertex, and I will edit this now because we need a normal and not a color anymore. So like this, we have one vertex. And how many vertices do we have? Well, we have 3 per triangle, so we multiply this by the amount of triangles and by 3. So that's the amount of bytes we need for the OpenGL buffer. So basically to store this here. And now what I like to do is just tell him or it that the buffer will be of this size, and then I don't give it anything. And afterwards I will use this GL map. Wait, how is this GL unmap? I don't know how the command was called. I forgot. Oh, okay. So I like to use this command here. And how this works is we basically we just give it the so here we told it how many bytes there are in the vertex buffer object, and then we tell it to unmap the buffer. So basically it will create a region of memory that we can write the stuff into. And in the end, we will just say unmap, and then it will fill in the stuff and put it into the graphics card. And for this stuff, I only need to write. The memory. And we get the void pointer here, but we want vertices. So now we have an array of vertices. So OpenGL allocated this for us. And then at the end, when we are done, we can call unmap. Where does it say that? Oh, yeah. Probably here, right? Yeah. Yeah, that's how it is. Wait. So, and once we call this here, OpenGL will take the contents of this buffer and put it to the graphics card. So now we need to fill the buffer, and for that we need to loop over the triangles. Yeah, I mean, it's basically the loop we have here. So this one here, no. So yeah, then we have one triangle, and so we need to create a vertex now. And then we can set the vertex position to be the mesh positions at, and then we take the index of the triangle position indices at the index we are interested in. And I think this works. So, and the last thing we need to do is, of course, put the stuff in the buffer. And I actually think wait, whatever. Vertices. So we need to put the vertex in its place, and to keep this pointer at an so I could either use an index here and calculate the index that I need to put the vertex into. Or what is possible too, we can dereference this and like keep the pointer updated. So after each vertex, we just move the pointer one index further. And I think that's actually it. So that's the same because the size of the vertex buffer didn't change. So I mean, that's actually how I do it in my game. And the thing is, somehow I have to put the data to the graphics card, right? I mean, so what do you think? How would you approach this? So I think this still works. And basically we have a function that puts our mesh to the GPU. And so MeshToOpenGL cube mesh. No. I don't think that's a stupid thing to think about. I mean, it looks really slow, but yeah, I mean, I thought about this too, but in the end, then I was like, okay, I mean, I need to get the data to the GPU, so yeah. Yeah, I like this map buffer too, because I don't need to create an extra, like, I don't need to care about the memory allocation, so that's really nice. Yeah, so the mesh is now in the GPU, and to draw it, we just need to enable the bind the VAO of the mesh, and the amount of vertices we're going to render are 3 times the triangle count. And the only thing, but I think this could already work. Of course, it doesn't if I made some errors. I forgot the I again. Okay, mesh data. Yeah, so that's not necessary anymore. Oh. Cube mesh dot. Okay. And there's our cube. Nice. And the faces look strange because the color, so previously this was our color, and now I put the normal information in it. So yeah, what you're seeing here is actually the normals being interpreted as colors. And of course the negative normals are black because they are clamped to 0. So we need to edit the shaders now. Let's see. Yo. Okay, so this is not a color anymore, this is a normal. And the frag normal is then just a normal, and we need to use the normal here. Wait, what the fuck? Okay. A software renderer? Oh yes, that sounds very painful. Yeah, I would say we could color the mesh in the way the normals are colored, but that's what we already did, so yeah. But we can use a bit nicer colors if we do this. Oh. Oops. Drag N. So now we can also see the other negative normals. Yes, and maybe I also want to add a ground. So let's use a plane. Plane, export. And we also can write a function to render a mesh. Or yeah, I don't know, render mesh. So we can just use this code here. Render mesh, cube mesh. And then this and this. And now I can just load a second mesh really easily. Maybe I can also create an array of meshes. So the first mesh is the cube and the second mesh will be the plane. And then I need to put into the GPU. And now I can draw the plane and the cube. And I think we won't be able to see the plane because it's inside of the cube. Yeah. Yeah, but here's the plane. So another thing I want to do, of course, is add a model matrix. Because I obviously want to move the plane and the cube and scale them, for example. So I need to add another uniform variable. And the thing is, so first of all, I just want to translate the plane. A bit downwards. So, and to use this when rendering, I want to pass this into the function. And I'm sure so I don't want to move this. Okay, so and now I need to put these into the shader. So this I can do here. And I think this could already work. Nope, because I don't have the shader here. That's very sad. Well, okay. Oh, okay, I swapped these. So I moved the cube instead of the plane. But it worked. So here's the plane and here's the cube. And now we might even want to scale the plane because it's a bit small. I just forgot the function. Scale. Where's the scale function? Okay. So maybe by 10. Oh. That looks sad. So the problem was that this returns a 3x3 matrix and I can't multiply a 3x3 matrix with a 4x4 matrix, so I need to convert this to a 4x4 matrix first. But now we have already a nice plane and a cube. Yep. Okay. So let me think about what to do next. Yeah, I could also input another uniform variable that determines the color of the object. And then instead of the normal color, I just put the color here. And this could be another argument to the function, to the render function. So are there vector 4s? Yes. So input them again. Uniform for FV. And I think this could work. Well, let's see. Okay, I need to add a color. And when using colors, the last argument is often just the alpha value, so how transparent the object is, or how opaque the object is. So if it's 1, it's fully visible. Syntax error. Oh. Yeah, so now they have a bit different colors. And now I want to implement some basic shading. And so normally, or in the earlier days of computer graphics, something that was used was the Phong lighting model. So like Kari mentioned previously, so there are different ways to render something. Of course, you could write any shading model here, but you might want to make it look as realistic as possible. And there are a few things you can do. In the earlier days, you often use the Phong lighting model, and nowadays you often use something like PBR, physically based rendering, which uses a lot of equations that try to model the real interactions of light in the, like how it occurs in the real world. But that's so first of all, the equations are a bit more complicated, and second of all, it takes a bit of time to implement this, so this is not trivial. And so I tried this once, and it's actually, from my perspective, it was really hard to say if I even implemented this correctly. So yeah, this takes a bit of time, and that's why I don't want to do this right now. So instead, I want to use a really simple model like this Phong reflection model. And basically how this works, yeah, hello Ghost. So how this works is we have so if you look at an object in the real world, you can kind of see that it might look something like this here. So even if an object is in shadow, like the sun isn't directly pointing at it, it still has some color because the like it's still lit by the environment, by the light bouncing around in your scene. So there's this ambient value, which basically says like how much is the ambient lighting of the scene. yeah, so that's basically kind of like a the minimum lighting that your scene has. But there's no direct, because it's just a general lighting information. There's no direction or anything, so it just gets a bit colored. But there's no, you can't. It's like in the game. It's like in the program currently. You can't really determine the structure of the object by looking at it, because you know these edges aren't visible here. So that's basically ambient lighting here, just a constant color. But if you have a light, like the sun, for example, you can then get some sort of direction into the lighting. And if you imagine, wait. So if you imagine you had like a surface and you had a torch or a flashlight. A flashlight is a better example. So this is your flashlight. And let's say for a second that the flashlight, maybe it's more like a laser pointer. There's only light in this cylinder here. And if you think about it, what happens here, if you point the laser directly from above, like perpendicular to the surface, then you have this region here that is being lit. But if you then turn your laser pointer, then this area here gets it gets wider. So if this here was like, I don't know, A, then this would be, this area here would be a bit larger than A. Maybe there's a better graphic here. I need to think for a second. Okay, so I don't know. I can't think of it, but maybe. Yeah, I don't know how to draw this exactly right now, but basically the area here increases, and as the angle gets like very steep, then you can see that the area here is really huge, and this area scales with 1 over the cosine of the angle that you turn the flashlight or the laser pointer. So yeah, I can't think of where this cosine, but basically the cosine is from this somehow you can derive the cosine term from this picture here. And what you will see then is that for a single point on the surface, so if you just look at this point, of course, the intensity of the light that this point gets is like is like 1 over the length of this, because the photons are hitting on the surface, and basically the further the photons are distributed on the density in this ray here is always the same, but when they reach the surface and the surface is larger, the density decreases, and as the angle gets really steep, you can see that the density is really low. So how much light 1 point reflects is basically proportional to the cosine of the angle between the light vector and you often do the light vector like this, and the normal vector of your surface. So if we were to draw this a bit more, so this is the normal vector, and this, for example, if the directional light was here, the light vector points into the direction where the light would be. And this is the angle between the two. Then you can see that you could get the intensity at this point, basically by using the dot product between the normal vector and the light vector. And that is that is basically this part, the diffuse lighting. So if the light vector, if the light points directly at the surface, the cosine of the angle will be 1. So the surface is fully lit, and if the light vector points like 90 degrees, then the cosine of the angle will be 0. So there will be no actual density of the light reaching this point. So then there will be no light, and everything will be in between is some amount of light. And if the cosine of the angle gets negative, then there would still be a value, of course, that's negative, but you would just clamp this to 0, but because lighting a surface from behind doesn't make really any sense. So if you were to point a light here, this side of the surface wouldn't, of course, lit up. I'm not sure if this was actually a very good explanation, but yeah. I just want to implement this right now. So I need a light vector. Yeah, so first of all, I want to add this light direction. Which is of course constant for all objects. And for example, so I want the light to point downwards. So maybe -1 in y direction. And to not get an extremely boring image, I want to get this a bit into the other directions too. And now I want to get the normal of the face. So this is this one here. And because we are interpolating the normal over the triangle. So basically, if you were to look at a triangle from the side, wait, like this here, for example. So this one here has a normal. So this is a vertex and this is a vertex. And in theory, here would be a vertex too, but that's now at this position because we are looking at it from the side. So what you can notice is normal vectors need to be normalized. So they must have length 1 to ensure that the math is working correctly. But if you were to take these normal vectors here and interpolate them, you would see that at this fragment of the triangle, this normal would have a length that is smaller than 1, because basically that's 1, and I mean you can kind of see that that's smaller than 1. So we need to re-normalize the vectors once we interpolate them to the fragment shader. And the same thing we can do for the light vector. And because I defined the light vector to be in the direction where the line should shine, but the actual light vector should point into the direction of the light. Because you always want to imagine this picture like here. You have your fragment, and then you have your normal vector and your light vector. So we could think of an ambient value, ambient lighting value, for example 0.2, and then we could also pick a diffuse value, which is now just the dot product between N and L. And because this could be negative, like I tried to explain on this side here, no, here. We also want to clamp this to 0 if it's negative. So we take the maximum. So if this is negative, then 0 will be larger than minus. So this will pick the positive at least 0. That's what I wanted to say. Yeah, and what I like to do is now, I don't know if this is actually how the real, I think the real Phong model just adds these two values, so ambient and diffuse, like intensity, and then it just does intensity times color. But if you diffuse value, if your diffuse value would be 1, then you would have a value then greater than 1, which would look a bit weird. So what I often like to do is just we have our diffuse lighting value, which is from 0 to 1, but I want to transform this value to be from the ambient value to 1. So this way there isn't a hard edge when this value, when ambient plus diffuse is greater than 1, because the value would be cut here at 1, because it can't display a value greater than 1. Hello, Vicent. But I think we're almost done. Yeah, so how I convert this into this range is basically I just multiply diffuse by 1 minus ambient, and then I add ambient, because this way 0 gets mapped to, so the value of 0 diffuse gets mapped to, so 0 times anything is 0, gets mapped to 0.2 from the ambient part, and the value of 1 times 1 minus ambient is 1.8, and then plus ambient is 0.2, so that's 1. So that's exactly the range that I wanted to get. All right. So I think this should work. Whoa. Maybe I misspelled. Oh no, I put the wrong. I want to send 3 flows instead of 4. Lerp, yes, I think I could use lerp too. Wait. Oh, it's called mix in GLSL. yeah, okay. Yeah, so I could implement this as mix. Yeah, so the start range would be ambient and the end range would be 1. And the interpolation value would be diffuse. Yeah, I guess maybe this is more descriptive actually. Yeah, that's a good point. Okay, so yeah, that's basically diffuse lighting. And I don't actually like the specular lighting because it always looks like, I don't know, it looks like plastic. I already like how this looks. So I will just keep it at that. Yeah, but basically the specular part is plastic. The specular part is like when you have something that is reflective, like something that is polished or something. Yeah. I think something that is polished would be a good way to describe this. And the way you compute these specular highlights is you also need, instead of just the normal vector and the light vector, you also need the view vector, because of course this is almost an exact reflection of the model of the light. So you want to compute the specular highlight, you want to compare how much of the reflection. So basically, if you reflect the lighting vector, the actual input lighting vector at the point you are interested in, then you would get the reflection vector, and you would then compare the view vector, so from where you are looking, with the reflection vector to get the intensity of the specular lighting. So basically, if these vectors would be the same, then you would get full intensity specular. Why does math on Wikipedia always look complicated? Yeah, the dot value increases to... So what exactly are you talking about right now? If you want to add outlines to objects for nicer visuals or just better visibility, I found a really nice method. Yeah, you can do that. By the way, I have a Discord server, so if you want, you can share this there. Maybe I will probably put the link of the Discord server in the description of this stream. But if you want to join right now, it's in a comment of the last stream. So yeah, so you can either you can either compare the view vector with the reflection vector, or you can compare the halfway vector, which is basically the vector exactly in the middle of the lighting and the view vector, and compare it with the normal vector. And supposedly that gives better results or something. I don't know. I mean, it's really just an approximation of what reality looks like. So yeah, you use a lot of hacks. I assume this is the difference here. So this is if you were to compare the reflection vector with the view vector. And this is if you were to use the halfway vector, I think. Yeah. So here he uses the reflection vector and dots it with the view direction. And because if they are equal, this value will be 1. And then they clamp it again. And this power factor here is you use it to sharpen the reflection. Because if this is your angle and this is your intensity, so here's the angle and this is the intensity. So this would look something like well, actually, I don't know what this would look like, but it would definitely be 1 here and 0 here. So here is like, no, wait, the angle is 0 here, and it is like, for example, 90 degrees here. And maybe it would look something like this, I don't know. But if you now power this function, because this here is 1, so multiplying these values with themselves basically gets you a sharper curve. And this is basically, you can think of this like the radius of your the radius of the reflective highlight. So you would, by increasing the power number, you would sharpen the highlight so it's smaller and more intense. But yeah, so I don't want to implement this because I don't like how it looks. So yeah. Okay, nice. And we get this value as a factor for a light amount, is that right? Yeah, exactly. So we dot the normal vector with the lighting value to get the intensity of the light that reaches the point we are interested in. Okay, so the last thing I want to do is I want to add the colors of that I used in earlier versions of the game, because I thought they looked nice. I just don't know. I just don't know them anymore, so I have to look them up. Let's see. So I think I used this as a background color. So basically the clear color that we put into OpenGL, this one here. Yeah, so at least the background has a nicer color now. And then I need to, let's see. I don't think I have this color anymore. Wait. Oh, I closed the... Okay, and what I like to do too is instead of using a constant ambient lighting value, like 0.2, what I like to do is... oh, okay. Bye, Francis. Yeah, so the stream is basically almost over. I just want to... what I often like to do is use a different colored ambient lighting value, because what you often see is not some uniform gray color that is the ambient lighting value, but more like, because the sky is blue, at least that's what I think, is that the ambient lighting value is a bit more bluish. That's why I like to use a bit more of a blue color here. The only problem now is that I think I can't use mix anymore. Or wait. Oh, this could work too. Whoa. Oh. So realistic guy. I mean, Phong is really just it's not really, I wouldn't call Phong realistic. So now, I mean, I think it looks a bit more realistic, because like the sky is a bit is bluish, and yeah, I don't know. I think it looks nicer. But yeah. And I don't know how to get the... Yeah. No, I'm not going to implement a ray tracer. But that would probably be the right way, yes. And I don't remember the gray color here. Maybe I will look this up off stream. But yeah, that's basically. Or I have one other idea. So I could this one. Okay, this is gray too, but a bit more bluish. So dude. Maybe like this, I don't know. That's a bit too bright. Thanks. I'm glad you like it. Okay, maybe like this. No, that's still too much blue. I think that's almost the color of the... Maybe not quite. Yeah, but that works. I think that's okay. Okay, so yeah, the last thing that's missing now is of course the shadows here. But these, I mean, I don't have, this would take a bit of, let me order my thoughts. I think this would take another hour or something. Next stream tomorrow. I don't know about that. But yeah, okay, well, we'll see. Maybe you can convince me in the Discord. Okay, yeah, but that's basically the stream for today. Again, I will upload this to the GitHub. I think I haven't even talked about this too much. So basically here is the code for this repository. If you want to try it out, you can just clone this. And there are built-in instructions for every platform. The ones for Windows are a bit messy because I'm not sure how to correctly compile SDL, but I mean, it compiles, but I'm not really sure, for example, how to do this statically. And yeah, the library is huge and it's a bit complicated, and I'm really bad at using CMake. If the next stream will be out physically, yeah. So I had the idea to actually, instead of talking about the paper that I posted on the community tab first, maybe I can talk about the XPBD paper first, because that's the most that's the most important paper of my videos, so maybe I could talk about this, but yeah, I need to think about that again. So yeah, I will post this, and yeah. Also, yeah, I would for the XPBD paper, I would try to derive the formulas as best as I can. Also, this time I put a bit of music in the background. I think you can hear that, I hope, at least. You can tell me how you like that. Because I wasn't sure if this is annoying or something. And my idea was to not put this in the recording of the stream. Because if someone wants to watch the stream at the at 2 times the speed, then it might sound a bit weird. Okay. That's nice to hear. Oh, okay, and one last thing I want to mention. I don't know if anyone follows this stream, like watches it and programs it side by side, but at some point I fixed an issue here. Basically, after the first stream, I noticed that the Windows stuff was not building, and it was because in C++, I think this is not allowed or something, so that's why I put these here, but that's not in the stream, so that's why I'm telling you this right now. Yeah. But basically, that's it. SDL needs these attributes. But I mean, I don't pass them to SDL, so I'm confused. I think it was even an SDL error, which is even more confusing. But why? Because in C++, this version, in C only, this version compiles. But and only on Windows, it's really confusing. Okay, so yeah. Thanks for watching, everyone. And I hope to see you in the next stream. Bye.